Okay, let's look at a variable acceleration question, a bit of calculus, now MadAsMaths style. Okay, so this is another test of being able to really make sure we understand the difference between displacement and distance and how we can visualize them on a graph. Okay, so you're effectively given a velocity time graph, or at least a velocity time expression. You'll have to draw the graph. You're told the particle is passing through the origin when t equals 0. Okay. And then you're asked to determine the displacement of the particle from the origin when it has covered a total distance of 13 meters. So, the idea is this: displacement and distance are sometimes the same, and sometimes they aren't. It depends on the direction in which an object's moving. And the idea is, you need to think, right, when this thing has travelled a distance of 13 meters, what is its current displacement? If an object just moved in a straight line without turning back on itself, then the displacement would be 13 when the distance is 13. However, this object with this expression presumably is changing direction. Okay. The way you want to do this question is you want to draw this velocity time graph and consider the areas under the graph. And there'll be several areas under the graph. It won't be a simple case of one. There'll be multiple. And think about, how does the displacement and the distance change as I increase time? Can I find when the distance is 13? At what point on the graph will the distance be 13? And then correspondingly, what will the displacement be? So please start by drawing the graph for this one. Okay. Once you've drawn the graph, try and find where the distance is 13. A bit of integration, you're going to need that. And then see what the displacement might be. Okay, so give this one a go. Pause the video now. Okay, so I said we had to draw a graph, so let's draw it. The equation is velocity equals a half t squared minus 3t plus 4. Okay, and time is greater than or equal to 0, it makes sense. So to draw this, let's think about some key values. When t is 0, the velocity is naturally 4. And we should be able to factorize this expression. Now I did this earlier. As it turns out, let's just write it here for a moment. V, that expression there, that's the same thing as a half times, what did I get? Actually, just to make sure I don't make any mistakes here, I'm just going to write a little bit more fully. So a half t squared minus 3t plus 4, if I equate that to 0, that's the same as this, which quite easily factorizes. And therefore I have that t equals 2 and 4, okay, when the velocity is 0. So therefore I've got a few points here. So from that, I've got the following point, let's say here, at 0, 4. And then from these two, which is when the velocity is 0, I've got a point at 2, 0, and another one at 4, 0. And just very quickly, let's just do a very quick derivative, dv over dt. That's going to be equal to t minus 3. And when that's equal to 0, t equals 3. So that was me just finding a stationary point very, very quickly. So therefore when t equals 3, it's going to have a stationary point. We can tell it's going to be we can tell it's going to be, oh, hang on. Yeah, a minimum in this case. Because the coefficient of t squared is positive, therefore it's a U shape. So it's going to have a minimum. So that's at t3. And if you plug 3 into here, I believe you end up with minus a half. Okay, so we've got those points there. Let's join them up. Roughly speaking, we've got a kind of, very roughly speaking, we've got this U shape. Okay, I'm happy enough with that. Okay, because although this is a bit wonky in the curve, it doesn't really matter because this isn't really a key feature that we're going to be working with. So here's the thing. We're going to think about displacement and distance as we move along this blue line. Okay, so let me just see if I can get the concept right here. When I'm here, I have covered no area at all. Okay, when I'm say here, let's mark it on. Okay, I'm going to try and make this a little bit more thorough in my explanation. We've got this area covered here. Okay, so at this time, whatever that time may be, you know, based on this, it could be just a little bit less than 1. I've covered this much area of displacement. So this area corresponds to the displacement and it corresponds to distance. So they're the same thing at this point. Let's look at a different case though. When I'm at, let's say, this time, okay, what is my displacement and my distance? Well, my two areas, let's shade them. Okay, so that's my first area and that's my second area. Let's call them A1 and let's call this little bit A2. In this case, the distance is going to be the sum of those areas, but the displacement is going to be taking that first area minus the second area, because displacement has direction, so we have to take into account whether the area is above or below the graph. So now at this time the displacement and distance will not be the same. They were up until here, they were the same. Then after this point they start changing, because instead of adding this area or taking it away, or sorry, instead of adding it in both cases, now it's in one case I add the area, in another case I take it away. Okay, so that's the concept we're working with here. So let me just erase this and we're going to actually think now about some specific values. So I'm going to reuse those names, but I'll be very specific now. A1 is that full area there. Okay, it's that full thing. A2 is everything here. Okay, to find that we're going to have to do some integration. A1 is the integral of the function, which is a half t squared minus 3t plus 4 from 0 to 2. And A2 is equal to the integral from 2 to 4 of a half t squared minus 3t plus 4. Now, within the working, I'm going to just give you what the general integral is, the indefinite integral. That should be a 6th t cubed minus 3 over 2 t squared plus 4t. Let me just check that. Yes, okay, technically with a plus c. You can then use that indefinite integral to find these definite integrals. And I'm going to let you guys do that. I don't want to go through the full effort of working that out. Really, you can just use a calculator. Okay, you can pause now if you want to have a quick check, but otherwise I'll give you the answers in a few seconds. So in the case of A1, you get 10/3. And this integral here is going to give me minus 2/3. Okay, so really when I say A2 I want this area, I should have said A2 is the negative of that integral, which then gives me an area of 2/3. Okay, so the integral itself gives you minus 2/3, indicating it's something below the x-axis, but the area as a positive value, because area can only really be positive, is the negative of that integral. So negative of a negative gives me a positive 2/3. Okay, so let's just write them here as well to be clear. 10/3 and 2/3. Okay, So therefore, at this point here, let me just clear up a bit of space. So I was saying at this point here, what is the displacement and what is the distance? So let's just point at it with a little arrow. Okay, over here, this is t equals 4. Okay, the distance is what? It's the sum of those two areas. It's 12 over 3. And the displacement is going to be equal to the first area, A1, minus the second area, 2/3. So that's 8 over 3. Now 12 over 3, that's just 4. So let's change that to 4. Okay. Now we want to know what's happening when the distance is 13. So if the distance at this point is 4, then that means if we keep going along, let's just imagine some time period in the future at which the distance is 13. So in that case, what would the area be of that third area? Well, it's going to have to be 9, isn't it, to make it add up to 13. To get the distance 4, then an area of 9 gives me a final distance of 14. So if I just neaten this up a bit, let's say we go, actually let's just not do it completely to scale. Okay, so let's say, let's truncate it slightly. Okay, up to there, we've got an area of 9 in there. So now what's going on at this point? Or I suppose really I should say at this specific time. Okay, so the time is, I don't know, and I don't particularly care. It doesn't really matter. We don't know what this time is, but we do know that the distance is 13 because I'm declaring that this area is 9. And what will the displacement be? Well, the displacement's going to be whatever it was here plus the additional displacement that it's travelled within this area. Now this is a positive graph here, as in it's above the x-axis, so therefore displacement and distance are the same for this portion. So therefore we've gone from 4 to 13 by adding 9 area, and from 8/3 we can also just add the 9 to get our displacement here. So we'll end up with a displacement here of 8/3 plus 9, which is equal to 8/3 plus 27/3. That's just double checking on my paper here. I think that's 35 over 3. Yeah, 35 over 3. Okay, and that's it. That's matching up there. We've got a distance of 13, and we found the corresponding displacement, which is 35 over 3, or as I'll just give it to you as a decimal in case you've managed to do that, 11.6 recurring. Okay, that is the displacement when the distance is 13. It's not too complicated of a question as long as you can understand the difference between distance and displacement. And perhaps the tricky bit is the fact that this is not a displacement time graph, this is a velocity time graph. So it seems a bit unintuitive in the sense that you can't really visualize the displacement and distance very easily on the graph. So here I've said the distance is 4. It's hard to visualize the summation of areas, and it's hard to visualize the difference of two areas and then say the displacement is 8/3. But the calculus gets you there. Okay, cool. Hopefully you've had some luck with that. As always, please ask questions because these are tricky questions that I'm giving you to do. So if you don't ask, you don't get. So please make sure you ask me if you're having any issues. Cool. Okay, we'll leave it there.